Right, the next thing we're looking at here are examples of oxidation and oxidizing and reducing agents, and how do I identify them. So the first thing that I've got to have here in front of me is I've got to have my information. So I tend to always uh, make sure that I have my information in front of me. Like in this one, for example, I know that my reducing agent, my reducing agent, 1 second, is going to lose electrons and is going to be oxidized by Y. So it will become more positive. My oxidizing agent uh, gains electrons, and by gaining electrons, it reduces, Y is reduced by X, and it becomes more negative. So when I'm looking at these sort of things, I need to make sure that I keep the information that I have on hand. I make sure that I have my information with me so that when I'm working through all of the stuff, it's not something that's foreign to me. Alright, so let's have a look here. Let's look at the first example. Example 1. Let's look at example 1. Alright. The first thing I have here is they've given me Ca plus Cl2, and that's going to give me CaCl2. Right, now they want you to identify the oxidizing agent and the reducing agent. You have to show your calculation. So the first thing I need to do is remember my oxidation numbers. I know that if I have any atom by itself or any diatomic molecule, my oxidation numbers are going to be 0 and 0. I also know that when something bonds, it will either give up electrons or gain electrons in order to make that bond possible. So if I look at calcium here, calcium is in group 2, and it will give away 2 electrons, so giving it a 2 plus kind of charge. And chlorine will have a 1 minus. Now if I look at the relationship between these two, my calcium and my calcium, right, that's one connection. And I can see that my calcium goes from 0 to positive 2. So it tells me that it has lost electrons. And if it loses electrons, I know that I've got oxidation. Right? The second thing is I look at my other connection, which is the Cl2 to the Cl2 over there. And it went from 0 to negative 1. So here there was a gain in electrons, which means I have a reduction. This is how you work through these issues. All right, so I know that oxidation is loss. So I know oil, rig. I know that oxidation is loss and reduction is gain. So here's another way of remembering things. If the oxidation number, let's put it here. If the oxidation number goes upwards, it increases, then I've got oxidation. So it's a nice way or cheat of how we look at things. If I have reduction, if the oxidation number goes downwards, then I've got reduction. So that's a nice way of looking at it when you are working with this sort of thing. So the first thing we have to figure out is what is the what do we know about oxidation and reduction in this equation? What is being transferred? The second step that you need to do is you need to write down those oxidation numbers. So I did that there. Right, there's step 2. Step 3, you need to make a decision as to what was oxidized and what was reduced. And this here is our little cheat of how things work. Step 4, we actually need to look at the situation. So if I look at CaCl2, I know that I have my calcium that transferred 2 electrons in this whole process. All right. So in this situation, the calcium loses electrons, and it gives its electrons And this is just my first example, so it's going to be in detail, to Cl2. Right? And by doing that, it allows the chlorine what am I doing? To become reduced. So it's going to become less. Now, by giving electrons, it allows the Cl2 to gain electrons. By doing that, allowing it to become reduced, we can say that calcium is the reducing agent, and that calcium was oxidized. All right. If I look at the chlorine gains electrons, right? It takes electrons, this is important, from the calcium, but by doing that, by taking the electrons from calcium, it allows calcium to become oxidized. And by allowing that, it allows Ca, calcium, to lose electrons. And by allowing such a thing, we can say that chlorine is the oxidizing agent because it was reduced. And that's how we look at something like this. Please make sure you get down these notes and this information, because when you're going to be studying for exams, you need to come back somewhere. And the best place to come back is worked examples. And when we do worked examples, it helps us to see how we got from A to B, or how do we get there, so that when I'm studying, I have a way of functioning. So that was example 1. We're going to now look at example 2. All right, this is example 2. We've got here nitric acid plus hydrogen sulfide to give me sulfur, nitrogen monoxide, and water. So that's the equation. Right. The first thing you need to do is you need to find oxidation numbers. Right. Now, when I want to find oxidation numbers, I must find out for every atom. Very important. So when I'm looking at this sort of setup, let's look at HNO3. I need to make, now HNO3 is a compound, so its charge at the end should be neutral. So let's have a look. I know that in any compound, hydrogens must be +1. And I know that oxygens must be -2. But you don't just have -2. You have 3 of them, right? Let's do that a bit differently. This must be -2, and that's times 3. So technically, you've got -6 and +1. So the only thing that nitrogen can actually be there is +5. All right, the next thing is hydrogen sulfide. But hydrogen sulfide, you know of hydrogen that it must be +1, and you have 2 of them. So technically, your charge here is +2, but you know nothing about sulfur. But you do know that your compound must be neutral. So the only thing that sulfur can be is -2. Sulfur, when it's by itself, an atom must be 0. Then you have nitrogen monoxide. We don't know anything about nitrogen, but we know about oxygen that it must be -2. And if that's -2, then nitrogen must be +2 for it to be 0. Then the last one you've got there is water. And we know that in water, oxygen will always be -2, and hydrogen will always be +1, and you have 2 of them. So it kind of works out and it cancels each other. So that's the first thing that needs to be done. So we've done that. We do this above the equation. Right. The second thing that we look at is we need to find the change. We need to find the change in oxidation numbers. Right, so how we do that is we just compare. Right, I know that I've got hydrogen, I've got nitrogen, I've got oxygen, and I've got sulfur. Same thing on this side, right? So on the left hand side, so I've got the left hand side and I've got the right hand side. On the left hand side, my charge of hydrogen is +1. My charge of nitrogen +5, oxygen is -2, and sulfur was -2. On the right hand side, my charges of hydrogen was still +1. My charge of nitrogen was now +2. My charge of oxygen was -2 and -2. So I'm looking at the nitrogen monoxide and the water. And then the sulfur was 0. So when I'm looking at these, I need to find the ones that there are changes. Any changes with the hydrogens? No. Any changes with the nitrogens? Yes. Any changes with the oxygens? No. And any changes with the sulfurs? Yes. Now we have to look at what happened. This nitrogen here, just highlight it for you, the nitrogen, right, and the sulfur here, they went through certain changes. So what we want to do is we want to look at what were those changes. So the nitrogen went from +5 to +2, which means we took away, we added on electrons. So I know that there was they gained electrons, and if something gains electrons, it means it was reduced, became less. So I can see 5 to +2, I'm getting less, which means the only thing that can happen if that happens is we added electrons. With the sulfate went from -2 to 0. So it's becoming, from here to here, it's becoming more positive. And when it's becoming more positive, we know that it loses electrons. And that means it's becoming, or we had, it was oxidized. So here I've got reduction, and down here I've got oxidation. So that is how we find out what is going on. So one of the things that makes this trickier is that the atoms which are getting oxidized or reduced are part of compounds with other elements. It's not just elements. They belong to something. So when they belong to something, there's a way in which we have to write this. So a limitation, not a limitation, but something that gets complicated is you need to note that atoms in these reactions, are attached to compounds. So they're not freestanding, right? And if they part, right, we can say they are part of a compound. And that makes things just relatively a little bit complicated. Now, previously we worked with atoms, but here's the thing. They, not just atoms, they bonded, the nitrogen and the sulfur. So we know that atoms are reduced or oxidized, but because they are compounds, we need to understand that the entire compound is being reduced. So when the atoms belong to compounds, I'm just going to move up here, right? When atoms are reduced or oxidized, oxidized, and they are part of a compound, we say the entire compound is being reduced or oxidized, right? Everything. So in this situation, let's look at oxidation. If I'm looking here at the sulfur, if I'm looking at sulfur, right, the sulfur I know is being oxidized because it lost electrons, right? I know that. So what's actually happened now is that I had H2S with a charge of 1 here and -2 there. What am I doing? -2 there. And that became S is equal to 0. So that is the sort of thing that happened. Now this sulfur, it had to give away the electrons. Now if it's giving away electrons, what is the thing that was receiving? Right? So what we can say, the first statement you must write down is the hydrogen sulfide is oxidized, not the sulfur. The sulfur changing its oxidation number just tells me where the oxidation is taking place. So when we write it down, we must write that hydrogen sulfide is oxidized because it has lost electrons. You must make sure that that is what your statement looks like. If you say sulfur is oxidized, it will be marked as incorrect if it didn't start off as an atom. Right, now, remember I said that this sulfur over here, oops, it's giving away its electrons. To whom does it give away the electrons? So I know that the sulfur gives the electrons, right, electrons to the nitrogen. But I know that the nitrogen doesn't belong to itself. So basically what I've got here, I'll get it like this. I've got H2S and I've got HNO3. And my sulfur, let's say my sulfur over there, is going to give away its electrons to the nitrogen. So I've got a situation where this sulfur, oops, undo that. The sulfur is doing something like that, and it's giving away, in this situation, 2 electrons. So what we're going to say is, we know that from this little table that we drew here, the nitrogen, right, was reduced. How do I know that it was reduced? It gained electrons. But remember, the nitrogen belongs to nitric acid. So it technically went from HNO3 to nitrogen monoxide. So that started as +1, +5, -2, and then this became +2, -2. Right? So what's happening here is that, in essence, the HNO3 is reduced because it has gained electrons. Right? And that's how that sorts itself out like that. Right, so now in this situation, we need to decide which is the oxidation agent or oxidizing agent. So what we're looking at then is, because the H2S, I can write a statement here, because the H2S is oxidized, right, it allows a reduction to take place, right? And if it allows that to take place, we must say that the hydrogen sulfide is the reducing agent. If I look at the HNO3, at HNO3 it's taking electrons, so it's becoming reduced, and by becoming reduced it's allowing oxidation to take place. So in essence, I can then say that the HNO3 is the oxidizing agent. And that's how you sort out that sort of information. You need to make sure that you work with these. Remember, another thing, these things here that are in brackets, right? All of this does not change the oxidation number. Does that make sense? So I can't see that O started off as -2 times 3 and it was actually -6. No, that's not correct. O stays at -2 and then it changes on the other side. This little thing over here is only there to help us find the oxidation number, the oxidation number of other atoms in a compound. But they don't actually influence it. That number stays as -2, or here it stays as +1. It stayed as +1, and you can see when I did it here, can you see? I kept it as +1. It's not automatically +2. Right? It's assumed that it's +2 when we do our calculations. Look here too. I kept that at -2. Right? So please make sure that you understand when we do these types of things, you can't just be changing all sorts of silly things. And example 3, it says use oxidation numbers to identify where redox reactions take place in the following reactions. So they've given us 3. The first one is sulfur plus oxygen gives me sulfur dioxide. So I've got sulfur plus oxygen, and that's going to give me sulfur dioxide. Right. So let's have a look. We want to know, is there oxidation, isn't there oxidation? Right, so let's use the first one. First, sulfur by itself, 0. Oxygen by itself, 0. Sulfur, when it joins in a compound, or oxygen rather, because we don't know anything about sulfur, but I do know of oxygen that it must be -2. But there's 2 oxygens, so times 2. Which means if that's going to be -4, sulfur has to be +4. Alright, so let's do a little connection. If I connect the 2 sulfurs together, I'll notice that it's going from 0 to 4. The only way that it can do that is there must be a loss of electrons. And if there's a loss of electrons, I know that it's oxidation. Right. If I look here at oxygen, to the other oxygen, it starts off at 0 and then it becomes -4. The only way that that can happen is if I gain electrons. If I gain electrons, it means I have reduction. So the question is asking us, do I have a redox reaction? So I can say that therefore A is a redox reaction. And the only way that I can do that is I prove this. So this little bit that we did now, it is NB. It has to be done. Let's have a look at the next one. Look here. Oops. Move that out of the way. We can move this there somewhere. Right, the next one that I've got here is I've got sulfur dioxide plus oxygen, and this gives me sulfur trioxide. Right, let's have a look at what's going on here. Right, don't worry about the subscripts, just worry about what's going on here. Now in SO2, I know that the oxygen must be -2, and there's 2 of them, so times 2, which means my sulfur has to be +4. Right, done. The next thing I have to look at the O2. The O2 is 0 because it's a compound. Then I've got SO3. Again, I don't know anything about sulfur, but I do know about oxygen. I know that oxygen must be -2, but this time there's 3 of it, so it's leaving me with -6. But I want it to be neutral, so the only thing that's going to cancel that out is +6. Right, so can you see how in working with sulfur, here it's +4, here it's +6. It's not always going to be the same. We've got to use the rules that we actually know about that can help. Right, so if I look at sulfur and I connect it to the other sulfur, it went from +4 to +6. Right, the only way that that's going to happen is if you, because it's getting, the oxidation number is going up. And if the oxidation number is going up, then I have lost electrons. And if that happens, I've got oxidation. Great. The other one I'm looking at is I've got two things going on. Let's have a look here. The first thing I have is I've got O2 and O2. Let's just connect here. I've got O2 and O3. Can we see that in the yellow? And then, this is another color. I use red. I've still got O2 here. And that's going to join up here. Alright, so let's see the two different things that's happening. So if I'm looking at the yellow one goes from the SO2 to the SO3. Now, if I look at the yellow one, it's -2 on this side and -2 on that side. So what I can see is that there was no change. All right. However, if I'm looking at the red one, I started off at 0 and I ended up at -2. So how did that happen? The only way that could have happened is if we gained electrons. And if that happens, I have reduction. Right, so another thing that I noticed here, and you're probably wondering as well, what happens to this? These coefficients. Right, I want you to make a note for yourself with the coefficients. The coefficients do not influence the redox calculations. So we don't have to worry about it. Do not worry about coefficients, right? Alright, so if we're having a look here, I've got an oxidation, I've got a reduction. I can therefore say that B is a redox reaction. Alright, and now I've done A and B, so I'm left with C. Let's have a look at what's happening with C. What you would have noticed is that the SO2, I can do it with a blue pen. The SO2 from A is actually, the product SO2 from A is actually the reactant from B. And the product from B, SO3, is actually the reactant of product of reaction C. Basically what you're looking at here is you're looking at the contact process. Because this whole process, these three equations, all have to do with the production of sulfuric acid. Right? It's the steps of how to produce sulfuric acid. All right, let's have a look at 3. I just want to do something. 3, just copy that. Move that here. Right, with 3, let's see what it says. It says there that you've got SO3 and SO3 plus H2SO4. See, there's this fix it a little bit. A second. SO3 plus H2SO4. So you've got sulfur trioxide plus sulfuric acid, and that's going to give me, it's going to give me something called disulfuric acid. Disulfuric acid. Right. So let's have a look now at how that's going to work. Okay. Oxidation numbers. With SO3, here it's -2 times 3, which is -6. So this is going to be +6. The H2SO4, I know that this is going to be -2 times 4, and this is going to be +1 times 2. And I want the whole thing to be neutral. So I've got -H here by the oxygen, and I've got +2 by the hydrogen, which means this sulfur has to become +6, right, to cancel that out. Then with the hydrogen, with the disulfuric acid, the oxygens must be -2 times 7 of them. The hydrogens must be +1 times 2 of them. Alright, so I've got -7, which is 14, +2, but I want it to be 0. So I need this value here to be +12. But look at how many sulfurs I have. Technically, I have 2 sulfurs, so this number must be divided by 2. So I'm left with +6 in that situation. Right, let's look at relationships. That was a bit of a tricky one, but let's see if we can make it work. Right, on this side, I've got a sulfur and a sulfur, right? But I've also got this sulfur and this sulfur. So in the first one, I had sulfur. This is how you split this up. Oxygen and hydrogen. My sulfur on the first side, it went from +6 and +6. Alright. And it ended up at +6 on the other side, on the left-hand side. So I'm comparing right-hand side to left-hand side. Right. The oxygens went from -2 here, and it ended up with also -2 there. And the hydrogen started off as +1 and ended up at +1. So if I look at the left-hand side and the right-hand side, I'll notice that for the sulfur, there were no changes. Oxygen, no changes. Hydrogens, no changes. Therefore, C is not a redox reaction. Right, and that's how you sort that information out. Alright, so the trickiest thing was this little bit here. I understand that. That's as complicated as it's going to get. So all you've got to do is make sure you take care of the subscripts. You don't have to worry about balancing equations in this section. You need to make sure that you sort out those oxidation numbers. Alright, the next question we're looking at is part of the same example. It says where redox reactions take place from question 1, or from question A over here, identify the reducing agents. So if I'm looking at A, I know that A was redox. And in A, I know that sulfur, so I'm only looking at reducing agents. When I'm looking at reducing agents, I need to see where the oxidation site was. So what was oxidized? Because whatever was oxidized, whatever lost electrons, is going to give me my redox reaction. So if I look at sulfur, sulfur went through oxidation because it lost electrons. So there was a loss of electrons. And because it was oxidized, it means that sulfur, if I look at the first one's nice because you can look at sulfur here. Can you see sulfur? By itself, doesn't belong to anything. I can say that the sulfur is the reducing agent. Right. If I look at B, I need to look at what was going through oxidation. So in B, I had oxidation happening between, I'm looking here, sulfur. Right, so I know that B was redox. Again, the sulfur was being oxidized because it lost electrons. Right, it lost electrons. But the sulfur itself in B did not belong to, and I'll highlight it for you. If I look here, it didn't belong to itself. It actually belonged to a compound, which was sulfur dioxide. So in this situation, the SO2 is the reducing agent. Now in exams, you've noticed they can say, give the name and formula. So you'd have to say sulfur dioxide. So SO2, sulfur dioxide, is the reducing agent. So that's how that works in this sort of situation. And we know that C was not redox, so we can't answer that one. What we do know about C, and you can make a note for yourself, is that C is a synthesis reaction. And please note, not every single thing that we do is redox. Right? So make sure that when you looking at these questions, you understand the difference between what is redox, what isn't redox, what is an oxidizing agent, what is not an oxidizing agent, and so on and so on. Example 4. Example 4 is 4 parts, right? So we're going to work through each of them. And these are how your questions are going to start coming across in grade 11. The first one says copper reacts with silver nitrate. Write down the half reactions and identify the oxidizing and reducing agents. So let's start with the first thing. If I'm starting with the first question, let's say that this is going to be question I, and this is going to be question 1 and question 2. Start with question 1. Oops. Right. We've got copper and silver nitrate. Right. The first thing that needs to happen here is you need an actual formula. You can't write half reactions if you don't even know what you're dealing with. Right. So the first thing we're going to say is copper, which is Cu, which is a solid, plus silver nitrate. Ag has a charge of 1 plus, and a nitrate is NO3, the charge of 1 minus. So you're left with AgNO3, and that is always going to be in aqueous. Now, you did a video on types of reactions, and you did single displacement, double displacement, synthesis, decomposition, and so on. Right. If I'm looking at this, I've got a single atom and I've got a compound. The only type of reaction that I can have here is single displacement, which means the copper is going to kick this silver out because it's more reactive and take the NO3. However, copper has a charge of Cu2 plus, right? So that means it changes things when it bonds with the nitrate here. So what I'm going to be left with then is Cu NO3 2 in aqueous plus Ag, which is silver, which is a solid. So the first thing you need to do when you write any of these down is you need to actually have a balanced equation. All right, so I've got my equation, but my equation is not balanced. So how I know my equation is not balanced, if I look at the NO3, on this side for the NO3, on the left and the right hand side, I've got 2 nitrogens and 6 oxygens. But on this side, I only have 3 oxygens and 1 nitrogen. So what I'm going to do is I'm going to put a 2 in front of that. And that changes my silver, so now that gets a 2. So now I've got a balanced equation. They want us to write half reactions. Now in order to write half reactions, the second step, so the first thing that needs to be done is you need a balanced equation, which we've got. The second thing that you need to do is you need oxidation and reduction. Now, we don't know if it's oxidation and reduction. And if it isn't oxidation and reduction, then that means we can't even answer B or A. So we need to first sort that out. So the first thing you need to do is then you need to actually write out your equation. So I've got Cu plus 2AgNO3 gives me CuNO3 2 plus 2Ag. Right, let's have a look at oxidation numbers. I know for the copper it's going to be 0. I know for the AgNO3, let's just have a look at this sort of situation. The first thing is for the O3, I know it's going to be -2, and there's going to be 3 of them. So I've got, so far I've got -6. If I've got -6, I need to see what my other oxidation numbers are. And I need to make sure that I look at my rules. So I know about silver. I know that silver, oops, what am I doing? Silver is Ag1 plus, because remember, with the normal metals, they take the charge or the oxidation number of their charge. In this one, it's silver Ag1, right? If it's Ag1, its charge is 1 plus. So this is going to be +1, which means I'm left now with the nitrogen. And the nitrogen, oops, has to be, this is -6, and then I have +1. The nitrogen has to be, oops, sorry, +5. Right, on the other side, I know that the oxygen here is going to be -2, and 2 times 3 is 6. So I'm going to have, oops. So technically I've got -12 over there. My copper I know is going to be +2, because I can see it here. It's a metal, so it will take that charge. Now what I'm left with is -12 plus 2 is -10. To cancel that -10, I'm going to need +10. So I need +10. Now if I look here at the nitrogen, can I see I have 2 of them? And positive 10 divided by 2 is going to give me +5. So that's the charge of the, or the oxidation number of the nitrogen. And the silver, because it's by itself, has to be 0. So if I look here, I've got Cu, I've got Ag, I've got N, and I've got O. So I need to compare left-hand side and right-hand side. So on this side, my copper is at 0. But on the other side, the copper is at +2. The silver here is +1. And on the other side, it's 0. The nitrogen is +5. And on the other side, +5. And the oxygen's -2. And on the other side, -2. So that stays the same. So what I can see here is that if I look at my copper, it went from 0 to +2. The only way to do that is it had to have a loss of electrons. And if I have a loss of electrons, remember, oil rig, I've got myself oxidation. Then with the silver, it went from +1 to 0, which means there was a gain in electrons. So I've got the reduction. Now with that, can you see the nitrogen and the oxygen? There are no changes. No changes. So they don't affect anything in this situation. Alright, so let's have a look then. Okay, so once you've got that set up, they want half reactions. Right, so the Cu, look at the Cu. How did it be? What happened to the Cu? So the Cu in oxidation, so the oxidation half reaction, the copper went from being copper to copper 2 plus 2 electrons. All right, because remember it's loss. So it must spit out. The Ag started off at Ag plus, then it had plus an electron. Oops, let's go back here. That's the reduction half reaction. Alright, so for the reduction half reaction, you had Ag1 plus, right, plus an electron. Those two will cancel each other, and I'm left now with Ag, because there was a gain. However, if I look at the gain that happened between the thing, in this situation, in terms of balancing, have a look here in front of the Ag. This is where the coefficients come in. Here, the coefficient, right? When we talk about the coefficient that's happening here, it was times 2, which means you went from Ag plus 2 electrons, and you ended up with, so you went from 2 Ag plus 2 electrons gives you 2 Ag. Right, so remember, the coefficients don't affect things in terms of oxidation numbers, but when we write half reactions, remember the half reactions must be, and I'll make a note for you on top here, your half reactions must be balanced. So you need to check the coefficients. That is why, if you have a look at step 1, we balance the equation. All right, step 2 was the oxidation and reduction numbers. All right, so you had to do the numbers, then you had to write the half reactions, and that was step 3. And now I have question A that's answered. Right, so when I look at the next thing, B says identify the oxidizing and reducing agents. So I know that in B, the situation was that for oxidation, copper went through it. Copper went through the oxidation. And for reduction, I know that the AgNO3, let's rather say that, the silver nitrate, because remember it's attached. Right, so the thing that's caused the oxidizing, the things that goes through oxidation will cause reduction. Alright, so it's opposite. So if this was oxidation, then therefore Cu, or copper, is the reducing agent. And since silver nitrate went through, or the silver went through reduction, we must say that therefore AgNO3, remember it's attached to, if I have a look here, can I see? It's attached to a compound. That whole compound, oops, undo that. Therefore, AgNO3 is the oxidizing reagent. The second part of the question says, chlorine is added to a solution of sodium bromide. They want, so this is C, I think, and D. They want the half reactions for this reaction, and they want the balanced net ionic equations. We're going to have a look at that now. Right, remember what we said the first thing is. The first thing you need is a formula. So I've got chlorine, and I'm going to add that to sodium bromide. But they haven't given me my products. So I've actually got to go ahead and actually write that down. So I know that chlorine is diatomic, so Cl2, which is a gas, plus sodium bromide. That's Na plus, and that's Br minus. So NaBr, and that is a salt. Now I can see I've got again an atom and a compound. The only type of reaction that can take place here is single displacement reactions. So what's going to happen is this chlorine is going to kick the sodium out, or rather pull the sodium away, and you're going to end up with NaCl plus Br2. Right, because bromine is a diatomic element. That's a solid, and bromine by itself is a liquid. Right, once I've got that, I need to make sure that it's balanced. If I have a look, I've got 2 bromines on this side, on the right hand side, 1 on the left hand side, so I'm going to put a 2 in front of it. By putting that 2 in front of it, I've caused a situation with the sodium. I can put a 2 there, and my sodium is balanced and my chlorine is balanced, so I've got myself a balanced equation. Right, now they want the half reactions. So let's have a look at how we're going to do that. So the first thing when we deal with half reactions, we need to look at the oxidation numbers. So if I'm looking at this sort of setup, I know that chlorine is 0. I know that when sodium is going to bond with bromine, it's going to be +1, and bromine is going to be -1. I know that when sodium bonds with chlorine, it's also going to be +1, and the chlorine is going to be -1. And then you're left with the bromine, which is by itself, which is 0. So if we connect all of these, let's have a look. If I connect this chlorine with this chlorine all the way, I notice that I went from 0 to -1. So when I'm going from 0 to -1, the only way that that could have happened is if there was a gain of electrons. And if I have a gain, I have a reduction. The number's getting less. If I look at the other connection, let's say I take sodium. I go from sodium to sodium. What you'll notice is that there is no changes. So which means I'm left with the last one, which is bromine to bromine. And it went from -1 to 0. So that number increased. The only way that's going to happen is if there's a loss of electrons. And that would mean that I have oxidation. Right. So right now, I need to write down my half reactions. So the first thing I can write is my oxidation half reaction. Right. My oxidation half reaction is bromine. Right. So bromine starts at -1. Right. But can I see how many I have of it? 2. So I've got to say 2 Br minus. Right. And what happened there was it turned into a neutral atom. So it turned into Br2. And how did it happen? By spitting out 2 electrons. So that's my oxidation half reaction. Then I've got my reduction half reaction. In my reduction half reaction, I started off with Cl2. And what happened to my Cl2 is it became -1. But I also have 2 of them. So Cl2 plus 2 electrons created a situation where I ended up with 2 Cl minus. So I can see here that there is a loss of electrons because it's spitting it out. And here I can see there's a gain of electrons because it's part of the reactants. And I discussed that with you in the very, very first video. So it shouldn't be giving you any issues in that sense. Alright, so now that you've got these two, the next thing they want you to do is they want you to give the balanced net ionic equation. Right, so I've got a couple of things. Let me put this down. I've got something called half reactions. Right, when I deal with half reactions, I must either have electrons in the reactants and I must have electrons in products. And when I have half reactions, it must be 2 of them, and one must be oxidation and one must be reduction. Right, that's the first thing. The second type of thing that I'm going to have is an ionic equation. An ionic equation, and we've seen it in the first video, is you take the equation and you write it out as ions. So everything must be written out as ions or as their individual atoms, if they were atoms. Or I can even say as individual diatomic molecules. Right? And the third thing you have is something we call a net ionic equation. With the net ionic equation, you need to have the ions involved from oxidation and reduction with no spectator ions. So those are the three types of ways in which we can write out these questions. So we're going to have a look now at how we're going to write this out. So in this reaction, let's have a look here. Please make sure you're taking down these notes. I can't stress how important this is. You had Cl2 plus 2NaBr gives you 2NaCl plus Br2. Right, this one here is just a normal balanced equation. Right, then if I had to write the ionic equation, that would look like this. So in another color. I have Cl2 plus, now remember, this here, to become that, they had to become ions. I have 2Na plus 2Br minus. Alright, that gives me again 2Na plus 2Cl minus plus Br2. That's an ionic equation. Now what I'm looking at is, when I looked at my oxidation numbers here, and I looked at sodium, what I noticed about sodium is that there were no changes, which means sodium is a spectator ion. And we discussed this in that first video, and I said to you that we need the spectator ion for the reaction to happen, but it is not involved in the actual reaction because it goes through absolutely no changes. So when I come down here and I'm busy writing out my ionic equation, in order to get my next one, let's see if I can choose a better color. If I want my net ionic equation, I've got to remove the spectator ion, which is the Na plus. So what I'm left with then is Cl2 plus 2Br minus gives me 2Cl minus plus Br2. And that would be my net ionic equation for something like this. Alright, so please make sure that you understanding what's going on, you're practicing, you're working through these examples. It's mostly just theory, and worked examples. And eventually we'll do some exercises on this. So the main part here is for you to get in as much information as possible. Right, let's have a look here. Example 5. Alright, when I'm looking at example 5, they're asking me for a bunch of things and I need to sort that out. So let's have a look here. It says, give the balanced equation, including states, half reactions, ionic equations, identify the spectator ion, net ionic equation for the reaction between aluminium and copper sulfate. Alright, so in this whole thing, we've got to do everything that we've just done now. If I were you, I would pause this video, then watch the thing so that you can see, can I do it? Right? Or if you don't know what's going on, you can just continue watching and let's have a look here. Right, the first thing that needs to happen here is I need to write out a balanced equation. So it makes sense for me to actually just sort this business of aluminium and copper sulfate out. First, with aluminium, there's a charge of 3 plus. Copper, they're telling you it's copper 2, so there must be a copper 2 plus charge. And sulfate, I know SO4 is 2 minus. So this information you should know just from the periodic table and from your knowledge of polyatomic ions for anions. So let's start writing a formula. So they want the balance equation including the states. So it says aluminium, which is a solid because it's a metal, plus copper sulfate, so Cu, and because the charges are the same, 2 plus 2 minus, it's CuSO4, and that's a salt which is in aqueous, will give me, now this is the nice part, we've done single displacement reactions, so I know that my copper is going to be kicked out, my aluminium is going to take on the sulfate. But don't forget, aluminium and sulfur don't have the same charges, so they must switch their charges. So I'm left then with Al2, SO4, 3, which is aqueous. Just reduce the screen a little bit. Plus Cu, which is a solid. So now I've answered question 1. Well, not really. I need a balance equation. So I've got the states, I need to balance. Alright, what I would have noticed is my aluminiums are not balancing. So I'm just going to, move this a little bit so that I can get that information in. Right, so my aluminiums are not balancing. There's 2 on that side. I'm going to put 2 over here. So just write that this is question 1. Right, another thing that's not balancing is if I look at my SO4, there's 3 here. And there's only 1 on the other side because I need 12. So 4 times 3, there's a 3 there. And that means the copper changed, so there's a 3 there. And now I've answered question 1, which is a balanced equation. Right, question 2. They want half reactions. But if they want half reactions, they want you to sort out oxidation and reduction. So the second thing that you need to do there is you need to sort out your oxidation numbers so that we can find out if it's what's reducing, what's oxidizing. So the aluminium starts off at 0. The copper here, let's just sort this out first. First of all, with the SO4, can you see that the SO4 stays in SO4 on both sides? So with the SO4, I know that the charge is -2, and there's only 1 of them, which means the copper has to be +2. That kind of worked out. With the aluminium on the other side, first I will need to work out with this SO4 because it's got the oxygen, so that needs to be sorted out first. I've got SO4, which is -2, and I've got 3 of them, which makes this value -6. So to balance that out, the aluminium has to be +6. So the reason I kept the SO4 together is because the SO4 contains oxygen, and it's all about the oxygen, right? So I could have, and because on the left hand side and the right hand side, the SO4 remains intact. It stays in SO4. And then I'm left with copper over there with a 0. All right, let's do some connecting. If I connect the Al and the Al, I've got that situation. If I connect the copper and the copper, that situation. And the last thing that I can join there is the SO4 with an SO4. So let's have a look at what I've got here. So I've got Al, Cu, and SO4. Right. On the left hand side, my aluminium was 0. But on the right hand side, it was +6. The copper, on the right hand side, it was +2. But on the left hand side, it was 0. And the SO4, it stayed -2 on this side, and it remained -2 on that side. So I can already see here that I have no changes. So that means my changes come from here. So for my aluminium to go from 0 to 6, what happened there? Right, the number went up. And the only way that the number is going to go up like that is if I have to lose electrons. So there was a loss of electrons. It means I have oxidation. Right, with the copper, It went from positive 2 to 0, so the number became less, which means I had to gain electrons for that to happen. It became less because I have reduction. Right, now I need half reactions. So let's have a look at what's happening there. The first thing is I've got Al, so I'm going to do let's do the oxidation. Oxidation, half reaction. Right, with the oxidation half reaction, I've got aluminium that started off at 0. And then what happened to the aluminium is it turned into, so remember here, so I just want you to make note, I said plus 6, and remember there's 2 of them. So technically each aluminium is plus 3. I should have told you that before. So it went from 0 technically to plus 3. Same thing happens, the lost electrons. So it became Al3 plus. And how did it stay neutral? It must spit out 3 electrons. Right, with the reduction, half reaction, remember there's a gain, so it must be on the side of the reactants. It was Cu2 plus 2 electrons, and that would have given you Cu solid. Right, so here I can see that there was a loss of electrons, and here I can see there was a gain of electrons. How do I see it? Look at the position. If it's gaining, it's part of the reactants, so it has to be part of reduction. Right, if it's losing, it must be part of the products, so I know that this must be oxidation. I'm saying the same things over and over because, as you may have noticed, things are getting a little bit hairy in these situations. So those are my 2 situations. My problem comes in that these reactions are not balanced, and oxidation half reactions must be balanced. What we mean by balanced, remember what I said. If my one reactant or my one atom is going to give electrons, the other one must be there to accept it. Now, in my oxidation half reaction, can you see that the aluminium gave 3, but the copper only gave 2? So these half reactions, they don't make any sense, right? So I've got to fix it. So I need to balance it. So when we do the next little thing, this is called balancing half reactions. And the goal in balancing half reactions is to make sure that the number of electrons is equal in both reactions. So when we mean both, we mean in the reduction and the oxidation. And now it's not. So what I've got here is I've got Al and Al3 plus 3 electrons. And I've got Cu2 plus, which, plus 2 electrons is giving me Cu. Right. The problem I said to you was that these 2 numbers were not the same. So what I've got to do now is I need to get these numbers to a common factor, or rather common multiple. All right, I need to find the highest common multiple. So the highest common multiple is 6. Right? So what's going to happen here is I have to take everything on each one, and I need to make it 6. So to make this 6, I need to multiply it by 2. And to make this 6, I need to multiply it by 3. But by doing that, I must multiply everything. So we're going to multiply by the highest common multiple. Right. So now I'm left with 2Al gives me 2Al3 plus 6 electrons. Then I've got 3Cu2 plus, where I keep doing that, plus 6 electrons gives me 3Cu copper solids. Now by doing that, this would be your oxidation half reaction, and this would be your reduction half reaction. Make sure it is balanced. Do not leave it unbalanced. Right, once you've got that situation, can you see that here the electrons, one's on the left hand side, one's on the right hand side, like an equation? We can cancel them out. Right, okay, let's not do that right now. But what you need to understand is, we're going to look at the next question. The next thing they want the ionic equation, and they want us to identify the spectator ion. Right, when we talk about, I think this was, oops, question 2. What are we looking at? Question 3. Okay. With question 3 is asking for the ionic equation. So we're going to take the ionic equation straight from the balanced equation. All right, so what I've got then, I want the ionic equation. And remember, it's all ions, just pure ions. And they want us to identify the spectator. All right, so let's have a look at that. So we've got Ag plus Cu2 plus SO4 2 minus gives me Ag3 plus SO4 2 minus, oops, plus Cu. Right, and that would be your ionic equation. Right, if we look here, and I see changes between Cu and Cu2 plus and Cu, and I see changes between Ag and Ag3 plus, which we already identified in the previous question. We know that therefore the sulfate ion, or you can write SO4 2 minus, is the spectator ion. Right. Another question that they could ask you is to identify, I'm just adding it here before we go to the last question, the reducing and oxidizing agents. And it's just an extra question that they could ask you, but it is helpful for us to do these questions so that we can understand and see what is happening. So I know that in terms of oxidation, the copper lost electrons and went through oxidation. But remember that the copper was attached to something. So if I look back here at my actual equation, my copper was attached to a sulfate. So it's not just about the copper, it's about the copper sulfate. So therefore, the copper sulfate, or CuSO4, is the reducing agent, because if it was oxidized, it creates reduction. With the reduction, I know that the silver gained electrons, right? And in that sense, it went through reduction, became less. But the silver was by itself. Remember, it was just an atom by itself. So here we can say that the Ag, or the silver, because it was reduced, is the oxidizing agent. So that's just an additional question that they could give you, but remember, we have to practice. Now, let's have a look at the last question you have. The last question they want the net ionic equation. So we're looking here at the net ionic equation. And we remember about the net ionic equation is that a net ionic equation must include everything that's participating. So this is number 4. This one here was number 3. Right, the net ionic equation must include everything that was actually involved. And the only things, and I can look here, the only things that weren't involved were the spectator ions. So we don't include that. The other thing that also happens, and we must make note for ourselves here, is that can you see that functions like an equals to sign? We've got the same thing on both sides of an equals to sign. They will cancel out. The electrons must be equal so that they cancel out. So I know that in a net ionic equation, I must only have ions which are involved in redox. I can't have any electrons, and I can't have any spectator ions. So then what I'm left with is, and remember I have a balanced equation. I've got 2Al plus 3Cu2 plus gives me 2Al3 plus 3Cu. And where do I take that from, or where do I get that from? I'm going to get this from the balanced half reactions. So if I look up here, let me just reduce this. If I can look here at the top, can you see? Reactant, 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 product, 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 product. And that's how I get a net ionic equation. I must use the balanced half reactions. I can't just be doing my own thing. I need to make sure that I've done the correct thing. All right, so please make sure that you practicing and so on. I might just do one more, and then after that you can move on to the next video. Right, the last thing we're looking at here is an activity. So there's a video that comes after this that will be redox reactions 5, but we're only going to do that next week. All right, so right now I'll upload the video obviously by Saturday or Sunday when I'm done with it. But for now, I want you to finish this activity, and I want us to mark on Monday. So you need to make sure that you're done with the videos and you're done with this activity, because when you watch Monday's videos, we amp it up a little bit. It's going to keep getting amped up all the time, and you need that stuff for grade 12. So you need to make sure that you are done with this work. And I don't want excuses, because I haven't overloaded you with videos. I've given you days, breaks, Monday, Tuesday, Wednesday. I didn't give you any work to do. So this work needs to be done. If you don't do it, it's your responsibility. I can't take responsibility for that. So the first question says, determine the oxidation number of the elements in each of the following compounds. Right, you need to show all working out, because I know that ions will have the charge of ions and compounds will have 0. I don't want to know that. I want the oxidation number of each of the atoms in each of those. Right, so that's the first thing that you're going to have to do. The second thing that we're looking at, it says identify the species that is being oxidized or reduced. So you're going to have to look at these questions and you have to find out what's being oxidized and what's being reduced. Once you're done with that, that should be relatively easy. The third thing that you're looking at is, would you use oxidizing agent or reducing agent in order for the following reactions to occur? So now you've got to think. If I have this sort of setup happening, how am I going from ClO3 minus to ClO2? What had to happen? And then would it be a reducing agent or oxidizing agent that causes this sort of situation? Right. Then the more intense part of this activity is you're going to look here at question 1 to 10. I'm just reducing the size so you can have a look at it. For each of the following elements, please, this is a bit lengthy, so please make sure you get it done. You need to identify the atom that is being oxidized and the atom that is being reduced. So I need you to identify what's oxidation, what's reduction. So you remember putting the oxidation numbers in and then making that decision. The next thing you need is the oxidizing agent and the reducing agent. Right? Notice there's an A in the middle all over here. The worksheet went a little bit wonky. And what that A actually means is an arrow. It changed the arrow to a symbol. I don't know why. Right. Also for each of the reactions, I need half reactions, ionic equations. Identify the spectator ion, and then I want the net ionic equation. I suggest you do all of these at once. So you write down the formula. So let's say you write down the first one. Mg plus 2HCl is going to give you MgCl2 plus H2. From there, you need to sort out the oxidation numbers. So I know that for Mg, it's going to be 0. Then for H, it's going to be plus 1, which means Cl is going to be minus 1. And then for MgCl2, Mg, I know that all halogens must be negative 1. So the Cl2 is going to be negative 1 times 2, which means the Mg is going to be plus 2 and the H2 is going to be 0. From there, you need to make sure that you find out what's oxidation, what's reduction, which is the oxidizing agent, reducing agent. What are the half reactions for each one? Are we adding 2 electrons, minusing? Are we adding 2 electrons? Are we spitting out 2 electrons? What are we doing there? What's my ionic equation looking at? What's my spectator ion? So what's not participating in all of this? And then at the end, what's your net ionic equation when you're done? So all of this is due on Monday when we're back at school. And I want to mark on Monday. Please don't disappoint me, because when you disappoint me, you're actually disappointing yourself. This work needs to be done. I'm doing my best. I've been working all holiday trying to get this stuff done. I expect you to do your work. So please make sure you get this activity done. I'm just going to go past the activities so that you can have a look again. If I were you, I'll just take a screenshot and then go off the video and sort that out. So please make sure that all of this work is done by Monday. And this is the last video for now. If you see redox reactions 5 and you're done with all of this, that's fine. You can go on, but it's not necessary. Monday we'll discuss what's going to happen next.